Okay, so this video is just going through some past paper questions on atomic spectroscopy, so the ones that you were set for homework. Even if you manage to get all of them correct, I hope that by watching this video you get a better appreciation of how to make the equations easier and also how to avoid maybe getting some errors due to rounding up in the calculations too early. So the first question I gave you focused on bromine, and it asked what frequency was needed to start a reaction. And you were told to use the data booklet to help with this. Now the reason for that is if you're going to start a reaction with bromine, what you need to do is break this bond. If you're breaking that bond, you need to have enough energy to break that bond. And if you look in the data booklet, the energy of that bond was 194 kilojoules per mole. And the question is, what is frequency? So now you needed to think about what equation do I know that links energy in kilojoules per mole to frequency. And the only equation that does that is LHF. L, Avogadro's number, is what makes it per mole, and H and F is what gives you energy values. Now, it only gives you joules per mole if you do it that way. And so we've got a mismatch of units. So in order to make this work, you can either turn this into joules by multiplying by 1,000, or you can divide this equation by 1,000, which turns that into kilojoules per mole. So there's two possible ways. Once you've done that, it's a case of putting in the numbers. So you can either rearrange the equation first, making F the subject, or you could fill in the numbers. I'm going to make F the subject first. So F is going to be E multiplied by 1,000 divided by LH. So that becomes 194 multiplied by 1,000 divided by 6.02 times 10 to the 23 multiplied by 6.63 times 10 to the minus 34. Now, I would put all of that into my calculator at once, rather than do the bottom part, round it up and divide. So what I would type is 194000, divide, then open brackets, put in all this multiplication, close brackets, and then press equals. If you're not comfortable doing that in your calculator and you do want to break it down into steps, I would, whatever value you get here, put it into at least 3 or 4 decimal places. Don't round up until the very end. So keep it 3 to 4 decimal places and then only round up at the end. When I put all of this into my calculator all at once, what I got was 4.86 times 10 to the 14 seconds to the minus 1, or seconds to the minus 1 is also equal to hertz. So you could do it that way. The second question in the questions that you got, question 2, talked about reaching a continuum, and it gave you a graph of frequency versus the change in frequency. And you had a curve like that. And it was basically saying at point 0, you're reaching n equals infinity. And there were a few different parts to this question. The first question was, what causes lines in an emission spectrum? Now, when it's an emission spectrum, you need to remember that is light being given out by the sample, not light being absorbed by a sample. And so in an emission spectrum, what's causing this is photons emitted as excited electrons fall. From higher to lower energy levels. Doesn't have to be falling to the ground state, just a lower energy level. If you said ground state, you'd probably get the mark, but it's more exact to say just to a lower energy level. Now the second question was, why a continuum? Why does that happen? Well, I'm just going to draw a wee diagram here, which is our nucleus here, and as we move out from it, we have n equals 1, 2, 3, 4, 5, etc. And you can see, as you move out, as your energy level, I'm not going to put your, as the energy level gets bigger, the difference in energy gets smaller. Or you could say, as the energy levels move further out, they get closer together. Now we need to relate it to a continuum, and a continuum is part of a spectrum. So we need to relate that information to our emission. And so to relate it to emission, we need to talk about as electrons fall from close energy levels, the wavelength or the frequency will be very close and hard to tell apart. If they're hard to tell apart, they will look like a continuum. Sorry, there's two U's in there. No longer discrete lines. So it is, need to make sure that we talk about understanding that the energy levels get closer together, but a continuum is not energy levels, it's to do with photons and it's to do with wavelengths. So we need to talk about emission, electrons falling, and their wavelengths will get closer and closer together until they're hard to tell apart and no longer discrete lines. Now, next question was to work out, well, at the continuum, so at delta E equals 0, and at delta E equals 0, that is essentially n equals infinity. You were told that the frequency was 1.26 times 10 to the 15 hertz. And you were asked, calculate the energy. E, and you were told E is in kilojoules per mole. So the equation we need to use, if it's kilojoules per mole, and we've been given frequency, E equals LHF, and that's in joules. To make it kilojoules, we need to divide by 1,000. So whenever you put it all together, 6.02 times 10 to the 23, multiplied by 6.63 times 10 to the minus 34 multiplied by 1.26 times 10 to the 15 all divided by 1,000. Now again, I would put all of that in my calculator at once. By putting it into my calculator all at once, I avoid any rounding up, and I ended up with 502.9 kilojoules per mole. You would be okay putting 503. I would always specify, if I'm doing any rounding up, if I've rounded it to the nearest whole number, or I've rounded it to one decimal place, to say. So I've done that to one decimal place. If the calculation doesn't say how many to round it up to, usually kilojoules per mole are to the nearest whole number. So nearest whole number or one decimal place is usually good. So that was part C1. Part 2 was, what does that energy represent? And it's this energy. What does that energy represent? Now that was the energy needed to get to n equals infinity. So if an electron gets promoted to n equals infinity, what's going to happen? Well, n equals infinity is the edge of the atom. If an electron gets there, it can leave. Essentially, it's got enough energy to no longer be bound by the nucleus. So that energy is the ionization energy. Every electron in an atom will have a specific amount of energy that takes it from its ground state to n equals infinity. And once you're at n equals infinity, you can leave the atom. And so you would be described, in that case, as your ionization energy. Now, question 3 that you had gave you a series of wavelengths, and it also told you that they were the Balmer series with everything falling to n equals 2. So there was a spectrum, there was a series of lines, and it said that this one was 656 nanometers, and this one was 319 nanometers. So you know that wavelength is bigger that direction. And it asked, that one was A, and it said this was the Balmer series, which is falling to n equals 2. If you're falling to n equals 2, it said what transition is happening. So essentially, what state, what energy level are you starting with in order to get here? Well, 656 is the longest wavelength in the series, and longer wavelength equals lower energy. And the lowest energy is the smallest transition. So if we're at n equals 2 and we are falling, it has to be n equals 3 going to n equals 2 to have the lowest amount of energy. Now the next question was calculate the energy. What is energy in kilojoules per mole for A? And that was a wavelength of 656 nanometers. Now with this one, we have got nanometers and we're working out an energy in kilojoules per mole. So the equation in this instance is E equals LHC over lambda, but that only works it out in joules, so that's joules. If we multiply by 1,000, we get it in kilojoules per mole. So that's our equation. Now here's where you can save yourself a lot of time, because this relationship comes up a lot. L is a constant, H is a constant, C is a constant. So E equals 6.02 times 10 to the 23 multiplied by 6.63 times 10 to the minus 34 multiplied by 3.00 times 10 to the 8 divided by 1,000 multiplied by lambda. Now when you do this, this is a constant, this is a constant, this is a constant. When you multiply them all together, you get an exact number. It's not a recurring decimal, it's an exact number. It is 0.1197378. These three things multiplied by one another get used a lot. If you do it once and can say this, so I suggest if you've got an exam, do this, LHC, and then just have that number written down. Saves you having to write out all of these or to do this multiplication over and over and over again. But it's 1197378. And then you're just dividing by 1,000 multiplied by the wavelength. Now the wavelength, can we use 656 nanometers? We can't. Because C is in meters. So we need to turn this into meters. 656 times 10 to the minus 9 meters. You might be tempted, because if you do physics, etc., to say, well, you cannot have 656 times 10 to the minus 9. You need to make it 6.56 times 10 to the minus 7. In chemistry, absolutely fine. In an equation, you can write that and you won't get any marks wrong. And it saves you from then having to worry about changing the power here. And then if we're multiplying by 1,000, again, multiply by 656, 10 to the minus 9, and it works out at 182.5 kilojoules per mole. So for this one, to save time, I would multiply those together. And because it is an exact number, do not round it at all and use it. And keep note of it, because probably in an exam you'll need to use this LHC 2 or 3 times. If you've already had it calculated once, saves you from having to do the calculation more than once in your calculator and make a mistake. Another really important point is you need to turn this into meters. You do not need to make it in proper scientific notation. All you need to do is take whatever this number is in nanometers and put 10 to the minus 9. You don't need to bother turning that into one number in units. It can be in the hundreds. That's absolutely fine. And remember that in order for it to be kilojoules per mole, this equation you need to divide by 1,000. So you get 182.5 kilojoules per mole. Question 4 gave you a picture of how essentially it said a sample was struck by high voltage and it emitted photons, and you ended up with lines, and each line could be a particular element. So tin was this one, and it had a wavelength of 284. The first question was, what region of the spectrum? Now, rules are 400 to about 700. That's visible. On this side, it's infrared. On this side, it's ultraviolet. When it comes to chemistry, you typically only be working with these three types of radiation. So the answer, because these values were below 400, it was UV. It then said to calculate the energy. So again, we are using what is E in kilojoules per mole. And we're starting with a wavelength, which was 284. So the equation is energy equals LHC over 1000 lambda. Again, that's nanometers. So it's 284 times 10 to the minus 9 meters. LHC, you calculated in question 3, so you don't need to bother calculating it again using your calculator. You can just say it's equal to 0.1197378 divided by 1000 multiplied by 284 times 10 to the minus 9, and that equals 421.6 kilojoules per mole. So remember, wavelength, just multiply it by 10 to the minus 9 if it's in nanometers. Don't worry about making it perfect scientific notation. And LHC, because we'd already worked that out in question 3, we can just write down that number again. It might seem strange to put a number to 7 decimal places, but it is an exact number. So you can do it that way. Question C asked for an explanation as to why that process of striking your sample with electricity gave rise to a spectrum. And for that, it is the high voltage sparking gives electrons energy, so they excite to higher energy levels as they fall, they release photons. Now specifically, because you were dealing with different elements and each element had a different line, you'd need to include a line saying wavelength is specific to different elements. And the reason why the wavelength is going to be specific is because based on the charge of the nucleus, the energy level values for each atom are going to be different, and if the energy level values are different, the energy transitions between energy levels is also going to be different for different elements, allowing you to tell them apart. Finally, we had question 5. Now, question 5 was talking about the Balmer series again, and it gave you this equation. So 1 over wavelength is equal to Rn, which it told you the value of, 1 over n1 squared minus 1 over n2 squared. where N1 equals the level it falls to, N2 equals the level it falls from. Now you were told in the Balmer series N1 equals 2. And you were told to work out wavelength for N2 equals 4. So that's what you were told. And what colour? So all you needed to do was to fill out the information. Now we were solving for wavelength. So 1 over wavelength is equal to Rn. Now Rn was 1.097 times 10 to the 7 meters to the minus 1. So we've got to be careful. We're going to be given a value in meters at the end of this. Multiplied by 1 over 2 squared minus 1 over 4 squared. So this is going to be 4 squared is 16. So 0.97 times 10 to the minus 7, 10 to the 7, sorry. A quarter minus a 16th, which a quarter minus 16th is 1.097 times 10 to the 7 multiplied by a quarter minus 1/16 is 3/16, which equals 205,687.5 meters. Because it is an exact number, I don't round it up. It didn't go on forever, it had an exact value, so I keep it. And that's 1 over lambda. So lambda is 1 divided by 205,687.5 meters to the minus 1, which equals 4.862 times 10 to the minus 7 meters. Now, wavelength, nanometers. So 1 meter equals 10 to the 9 nanometers. So if we multiply by 10 to the 9, we end up with 486.2 nanometers as our wavelength. Now I asked for the colour, and you were encouraged to look at your data booklet on page 20. Now, because this is an emission spectrum, we can use this directly. So we look at the colour wheel. 486 is here, so it's going to be green, the colour. 486 is going to be green. If it was absorption, we would use this differently, and whenever we get onto that topic, you'll see how. But because it's emission, we're seeing green, so the colour is green. And final question was the Lyman series is ultraviolet, and it asked what is N1 for that. Well, from the previous part of the question, the Balmer series is visible, and N1 equals 2. UV is higher energy than visible. And we know that because the wavelength is shorter. If the wavelength is shorter, it's got higher energy. The only way you can end up with higher energy photons, you need a bigger transition. And if we had n equals 2 as the transition here, the only bigger transition is if it goes to n1 equals 1. So it's falling a little bit further. You'll have more energy. So that's a common question. It'll either give you the Lyman series and ask you about the Balmer series, or give you the Balmer series and ask you about the Lyman series. The Lyman series is always falling to n equals 1, Balmer to n equals 2. If it's falling to infrared, that's going to be shorter energy, so that's going to be falling to n equals 3 or n equals 4. So hopefully that gave you an insight into how to approach these types of questions, and it will help you to answer similar questions better or quicker or more efficiently next time. So thank you for your attention to this video. I really hope it was useful.